is not heat, it's the humidity. Have you heard someone say that on a warm, muggy day? As we will see soon, there's a lot of truth in this statement. To understand humidity, you first have to realize that there is water in air all around you. But I'm not wet, you might say. That's true. Most of the air around you has water in the form of a gas called water vapor. Humidity is the amount of the energy or amount of water vapor in the air. So too much or too little humidity can be dangerous. For example, high humidity combined with hot temperature is a combination that can be health risk, especially for a very young and a very old people. Humidity plays an important role in our daily weather. Without water vapor in the air, our weather might be like the weather on Mars. When you hear weather forecasters talk about humidity, you might hear they talk about two different terms: absolute humidity and relative humidity. Absolute humidity is the amount of water vapor divided by the amount of dry air in a certain volume of air at a particular temperature. The hotter the air is, the more water vapor it can hold. Relative humidity is the ratio that a current absolute humidity to the highest possible absolute humidity, which will depend upon the current air temperature. Relative humidity is the term weather forecasters use the most often. A relative humidity of 100% means that the air cannot hold any more water vapor. It's totally saturated. When this occurs, it can rain. In fact, the relative humidity must be 100% where clouds are forming for it to rain. However, at the ground level, where the rain lands, the relative humidity can be less than 100%. So how does humidity affect us on a hot day? Humans are sensitive to changes in humidity because our skins use the air around us to get rid of moisture in the form of sweat. If the relative humidity is very high, the air is already saturated with water vapor and our sweat will not evaporate. When this happens, we feel hotter than the actual temperature. That's why we talk about heat index on chapter 4 temperature, remember? Likewise, very low humidity can make us feel cooler than actual temperature. This happens because the dry air helps sweat evaporate more quickly than usual. If the temperature outside is 75 degrees Fahrenheit, 23.8 degrees Celsius, humidity can make it feel warmer or cooler. A relative humidity of 0 would make it feel like it's only 69 Fahrenheit. On the other hand, a relative humidity of 100% would make it feel like 80 degrees. So, what's a comfortable humidity level? Studies have shown that we tend to feel most comfortable at relative humidity around 45%. Some people use special machines called humidifiers, add humidity or dehumidifier, remove humidity to keep indoor humidity at comfortable level. Since relative humidity is an important term we use to describe the water content of air, let's make sure we know what it means. Absolute humidity is the amount of water vapor present in a unit volume of air, usually expressed in kilograms per volume of air or in units of pressure. Saturation absolute humidity or capacity is the absolute humidity at a given portion of the air and could be saturated or not. The number depends entirely on the temperature. The warmer the air, the more kinetic energy and hence velocity the molecule have, the more saturated it can be with water. The cooler the air, the slower the molecules, the less saturated it can be. Air over the Great Barrier Reef or Australia is quite warm. Its capacity is high. Relative humidity, or RH, is a measure of how close the air mass's water concentration is to the maximum. Relative humidity is a percentage. What percentage of capacity has been reached? is the most useful measurement when discussing weather systems, because it tells us how much more water could be evaporated or how close it is to the rain. So let's use the figure to calculate the relative humidity. If you look here, you can see the saturation vapor pressure is 23.39 millibars. If the vapor pressure in the air sample is 10 millibars, how much is the relative humidity? So how you calculate this? Simply, you have the maximum 23.39 is the maximum capacity, but the air right now has only 10 millibars. So if you calculate, divide 10 by 23.39, you're gonna have the relative humidity about 42%. So compare those two elements you have. The water vapor in the morning in this left jar has maximum capacity where the temperature is 10 degrees. Now, in the middle afternoon, the temperature increased to 20 degrees, so like the air capacity to hold water vapor also increased. But the water vapor in fact is still the same amount, so now the relative humidity is about 52%. Later on, when the temperature reached 30 degrees, also the air capacity to hold water vapor increases. But the amount of water vapor is still the same like it was in the early morning. So now the total percentage represents only 28%. So if you look at the graphic in the right side, you see how relative humidity and temperature has different capacity. So while the temperature increase, relative humidity decrease. So I tell normally the rule of thumb. So if you put T in your right hand and you make it positive with your thumb, and RH in your left hand and also make the positive thumb, so they should go in the opposite way. So while the temperature increase, relative humidity decrease, and vice versa. Temperature decrease, relative humidity decrease. So that's a good example you guys can see between them. The temperature at which a given air mass with a given absolute humidity would reach its capacity or become saturated is called the dew point. In this graphic you see temperature across the bottom x-axis increasing to the right. On the y-axis we see absolute humidity measured in water pressure or concentration. The different curves represent different relative humidities, increasing as you move upward. The white arrow points up to 100% of relative humidity line. The red line shows that the temperature, 12 degrees Celsius, 100% relative humidity is reached when the water vapor concentration reaches 11 grams of water per cubic meter of air. At the same concentration of water but a higher temperature, such as 20 degrees Celsius, the relative humidity would decrease. What about the air mass at a temperature around 4 degrees Celsius? It would reach a 90% relative humidity or fullness at water vapor concentration or 5 grams per cubic meter, a concentration that would put 12 degrees Celsius at 50% relative humidity and 20 degrees Celsius air at only 30% of relative humidity. When we see clouds in the sky, we know the relative humidity air mass reach 100% and droplets of water starts to precipitate, usually around microscopic bits of dust of air. We're gonna talk that later.